Okay, thank you very much. It's a pleasure to be here in beautiful sunny Kelowna, which is a great change from rainy, dismal Toronto. I'm here today to present the work of my master's student, my former master's student, CWIT, who unfortunately could not be here today. What I'm going to talk about today is a new channel model, the delay selector channel, and some of the results from Lou's master's thesis, in which she found a nice closed form bound on the IID capacity of this channel. So just before I begin, I'd just like to comment, this is part of some new work that I'm doing. I'm doing something that's a little far afield for most information theorists. I've become interested lately in a field that's called molecular communication. So I'll talk a little bit about that as we get into the talk a little. Okay, so what is the delay selector channel? So the two motivations of this talk are defining this channel and secondly, obtaining capacity bounds on this channel. So what is the delay selector channel? Let's talk about that first. Well, let's suppose you had a channel that did this. There's a binary sequence, and let's say we want to transmit this across a channel. So what's going to happen is that the first input symbol that we drop into this channel, that 1, is delayed by a single time unit. And then it's dropped into the receiver right there. And each 1 that we drop into the channel can be delayed by a randomly selected amount. So that 1 is actually delayed by 2 time units. And it's dropped into the channel, as you can see there. This 1 is then delayed by a single time unit, and in that instance, what the receiver will end up doing is summing the channel input. So in other words, these 2, if you like, that channel input and that channel input will arrive at as far as the receiver is concerned, at the same time. Now, I'm only delaying the 1s, but because of the summing effect, you can see that in general, every channel input is delayed, although the effect of the zeros doesn't matter at the output, because what I'm doing is I'm summing the channel input, the channel outputs that arrive at the same time. So we can go on, that one will arrive there, let's say, that one will arrive there, and we will ultimately transform the transmitted sequence that we see at the top into the received sequence that we see at the bottom. So this is obviously a non-trivial problem to take that received sequence and from that guess what the transmitted sequence was. So systematically, this is what the delay selector channel looks like. We have inputs on the left, given by xi. We have outputs on the right, given by yi. There's nothing fundamental about this, but for the simplicity of our analysis, we've assumed that the inputs are binary. And what will happen is that xi will be randomly passed to one of these delay lines. The top delay line indicates no delay, so that's a possibility. And each subsequent delay line below it indicates a unit time delay. So this, the second delay line is unit delay. The third delay line is 2 units delayed. And ultimately, there is some maximum delay m. So in other words, there are m plus 1 possibilities that an input can be passed to one of these delay lines. At the output, we have this sum, this summation. What will happen is that if x is passed to one of these delay lines, we assume that the remainder are grounded at 0. And then the output, what happens is we just take the sum of all the channel uses that arrive at the same time. The channel parameters are qi. So this here we represent the random selection of one of these delay lines by a switch. qi gives the probability that any one of those delay lines is selected. So in particular, there are m parameters of this channel. Obviously, m plus 1 delay lines, the sum of the probabilities is 1, so therefore there are m degrees of freedom. For our purposes, we will assume that these selection probabilities are independent from channel input to channel input. So in other words, if my channel use right now is not delayed, that's independent of whether the next channel use is delayed. that can, of course, be generalized. So, let's think about some of the features of this channel. Firstly, obviously, it has memory. So that's interesting in and of itself. Channels of memory are known to be non-trivial, even in very simple forms. Secondly, it's discrete. In fact, it's integer. So the inputs are integer, the outputs are integer, and you can see that the maximum number of channel inputs that can pile up at the output is m plus 1. So if we have a binary channel, and the input is either 0 or 1, the output is on the alphabet from 0 to n plus 1. So, what's the application of this channel? The application is a new field called molecular communication. So what's this all about? Basically, this is what it's all about. The manner in which microorganisms communicate with each other is by exchanging chemical messengers. So this has recently come to the attention of nanotechnologists who are looking for solutions for communicating amongst devices at very small dimensions. So at very small dimensions, it's not obvious at all that the traditional ways that we think of communicating, for example, by exchanging electromagnetic fields, or by sending electrons down a wire, or by sending photons, it's not obvious that these scale very well to extremely small dimensions. Excuse me. So the question is, how has nature solved this problem? There are nanomachines in nature, and these are them. They're bacteria, they're everywhere, and they can communicate with each other. A simple example is something called quorum sensing. So, for example, certain species of bacteria will emit a message to their neighbors that basically says, "Here I am." And their neighbors will gather those chemical messages and use those messages to estimate the local population of their species. Another excellent example, in this room, there are thousands and thousands and millions and billions and possibly trillions of chemical messages being exchanged right now in the cells of your own body. This is exactly how cells regulate their own functions. So the vision of this work is this: tiny nanorobots swimming in the bloodstream doing interesting things. The particular interesting application that I often talk about when I talk about this is the following. So right now, the state of the art in cancer treatment is that we inject the body with toxins in chemotherapy that is just short of killing the person, but hopefully enough to kill the tumor. So if we could concentrate the toxic chemotherapy at a very high concentration at the specific location of the tumor, while not raising the overall concentration in the body to a high level, that would be very positive. And this is the vehicle by which we do that. These devices can swim, would hopefully swim within the human body, identify a tumor, call their neighbors. All those neighbors would swarm the tumor and directly inject a chemotherapy drug directly at the site. Now you may think that this is a far future, decades away kind of prospect, but in fact, the surprising thing about this science is that these nanorobots exist, and the problem is getting them to communicate. There's a researcher at the University of Montreal, his name is Sylvain Martel, and he's designed robots like this. And the problem is getting them to communicate and coordinate. So that's why this particular problem is so